Billions of stars are burning right now, pouring unimaginable amounts of energy into the cosmos. And yet, the universe itself is getting colder. This is not a contradiction. It is a statement about how physics actually works, and it reveals something about the future that changes everything. When this idea first crystallized in the mid-19th century, it disturbed the scientist who understood it most clearly. Rudolf Clausius, the German physicist who gave entropy its name, had formulated a principle so simple that it seemed almost trivial. In any closed system, disorder increases. Heat flows from hot places to cold places, never the reverse. Gases expand to fill available space. They do not spontaneously compress. Order decays. This was not presented as a rule imposed on nature by some external force. It was presented as an observation, a statistical inevitability that emerges from the sheer probability that disorder is far more likely than order. Clausius made a bold leap. If this principle held in every laboratory, in every furnace, in every system physicists could examine, then it must hold for the entire universe. The entropy of the universe tends toward a maximum. This statement carried implications so strange that even Clausius seemed to recognize the weight of it. If entropy always increases, if the universe is always moving toward greater disorder, then the universe must be evolving toward a state from which no return is possible. Eventually, all the energy differences that drive processes would disappear. Stars would burn out, planets would cool. Heat would distribute itself uniformly throughout space, and nothing would happen ever again. William Thomson, known to history as Lord Kelvin, arrived at a similar conclusion through a different path. He was not primarily thinking about entropy as an abstract measure of disorder. He was thinking about energy itself. Every time an engine runs, every time friction heats a surface, every time a photon travels through space and eventually gets absorbed, useful energy is being converted into heat. But heat, once distributed, cannot be easily concentrated again. A cup of hot tea cools in a cold room, but the room does not spontaneously heat the tea. This asymmetry was not mysterious, it was simply the way thermodynamics worked, but its implications were staggering. The universe, Thomson realized, was running down. Energy was being dissipated continuously, converted from organized forms into diffuse thermal radiation. At some point, far in the future, all the energy in the cosmos would be spread so evenly and so thinly that nothing would distinguish any region from any other. No temperature differences would exist. No heat would flow. No work would be possible. The universe would reach what Thomson called heat death. Neither Clausius nor Thomson was claiming this would happen tomorrow, or next century, or even in the next million years. The timescales involved were incomprehensibly vast. But the direction was certain. The universe, in this view, was not eternal and unchanging. It had a history, one that began in some state of remarkable order, and it had a future, one in which that order would vanish completely. For most people who first encountered this idea, there was a choice to make: either reject it as absurd or sit with the discomfort it produced. The idea that everything would eventually fade, that all human civilization and achievement would eventually be erased not by catastrophe but by the slow, remorseless spread of disorder, was not easy to accept. Philosophers and theologians struggled with it. Victorian sensibilities, which had developed a faith in progress and human improvement, found the concept deeply troubling. But what made the theory difficult to dismiss was that it did not rest on speculation about distant futures or untestable hypotheses about the cosmos. It rested on observation. Every time someone lit a fire and watched it burn down to ash, entropy was increasing. Every time heat escaped from a warm object into the cold surrounding air, entropy was increasing. Every time a chemical reaction went in one direction but not the reverse, entropy was increasing. The second law of thermodynamics, as it came to be called, was not a guess about how the universe worked. It was a summary of how things actually behaved, confirmed in countless experiments, in countless processes, in countless systems. Yet there is something strange about this picture when it is applied to the cosmos as a whole. The universe is not a sealed room. It is expanding. In the very early universe, shortly after what scientists now call the Big Bang, the cosmos was unimaginably hot and dense. As it expanded, it cooled. Regions of space that were once identical in temperature began to develop differences. Some regions became denser, cooler, darker. Others remained relatively sparse and hot. Over billions of years, gravity gathered matter into concentrations. Stars formed. They were hot. Planets formed around them. They were cool by comparison. The universe seemed to be organizing itself, creating structure, forming complexity. And yet, even as this organization was happening, entropy was increasing. This is the point where many people's intuition begins to slip. If the universe is becoming more organized, if stars are condensing out of diffuse gas, if life is emerging on planets, how can entropy be increasing? How can the universe be moving toward greater disorder while simultaneously becoming more ordered? The resolution lies in understanding what entropy actually measures. It is not a measure of how organized something looks. It is a measure of how many possible ways the microscopic parts of a system can be arranged while still producing the same observable macroscopic state. Consider a cup of cold coffee in a warm room. The coffee is organized, it has a definite shape, a definite color, a definite temperature, but the thermal energy in that coffee represents an enormous number of possible arrangements of the molecules inside it. Each molecule is vibrating, each one in motion, each one in a slightly different state. The number of different microscopic configurations that are consistent with the observation this cup is at room temperature is staggeringly large. Now consider a small spark of heat on the edge of that cup. The spark is very hot, but it represents far fewer possible microscopic arrangements than the cool coffee. If the spark dissipates and spreads throughout the entire cup and room, the number of possible microscopic configurations available to the system increases enormously, even though it appears less organized. This is what happens as stars form and burn. In the early universe, matter was hot and spread out. The number of possible microscopic configurations was high, but the energy was relatively uniform. As the universe expanded and cooled, gravity pulled matter together into clumps. These clumps became denser and hotter at their centers. When they became dense enough, nuclear fusion ignited, and stars began to burn. A star is a remarkable object. It is far hotter than the surrounding space, far more organized, far more intense in its concentration of energy. But creating a star did not decrease the entropy of the universe. It increased it dramatically. This seems backward until one considers what happens to the energy. When a star burns, it converts hydrogen into helium, releasing energy in the process. That energy radiates outward in the form of light and heat. The sun, for instance, radiates approximately 386 billion megawatts of power continuously. All of that energy escapes the sun and spreads out into space. Some of it is absorbed by planets, some by dust, some by gas. But most of it simply radiates outward, spreading across larger and larger regions of space, becoming more and more dilute, more and more dispersed. The energy that once was highly concentrated in the nuclear core of the star is now spread across an expanding sphere that covers an ever-increasing volume of the cosmos. That process, the concentration of energy followed by its spreading and dispersal, is the definition of increasing entropy. In fact, it is not the formation of the star that matters for entropy. It is what happens afterward. When matter collapses under gravity to form a star, gravitational potential energy is released. Some of that energy is used to heat the star to the point where fusion can occur, but most of it is radiated away as heat and light. Once that energy is radiated into space, once it is spreading across the cosmos in the form of electromagnetic radiation, it is effectively gone. It cannot be recaptured. It cannot be reconcentrated. It is available to do work only in the sense that a beam of sunlight can push on a solar sail or warm a piece of ground, but in the larger sense, it is lost. Entropy has increased. This is the key to understanding why the universe gets colder even as stars burn. The stars themselves are not exceptions to the second law of thermodynamics. They are mechanisms for increasing entropy. They take concentrated energy from gravitational contraction and convert it into dispersed radiation. They take order and convert it into disorder. They take a universe that could potentially be organized and drive it inexorably toward disorganization. There is a way to think about this that might make it clearer. Imagine a great reservoir of thermal energy spread uniformly throughout the cosmos. In the very early universe, shortly after the Big Bang, this reservoir was extraordinarily hot and extraordinarily dense everywhere. As the universe expanded, it cooled. But if the universe had expanded uniformly, with matter distributed evenly throughout space, it would have continued to cool toward a final state of uniform, extremely cold, extremely thin radiation. That would be the endpoint heat death, reached not through the burning of stars, but through the simple expansion of space. Instead, something different happened. Gravity broke that uniformity. Some regions became denser, others less dense. Those denser regions became hotter, and fusion began. The denser regions became stars. They burned brightly. They radiated energy into the space around them. But here is the crucial point. Stars burn hotter than the background radiation of the universe. When a star radiates, it is radiating heat from a hot object into a cooler environment. According to the second law of thermodynamics, this is exactly the process that increases entropy most efficiently. The larger the temperature difference, the greater the increase in entropy when that heat spreads out. So the universe was not organizing itself despite the second law of thermodynamics. It was organizing itself, creating stars, galaxies, complexity, precisely because doing so increased entropy most efficiently. The second law did not forbid the formation of structure. It actually encouraged it, in a statistical sense. A universe with stars and galaxies has higher entropy than a universe with matter uniformly distributed. The second law of thermodynamics is not a law against complexity. It is a law that determines which configurations are more probable than others, and a universe with stars and galaxies and complexity is more probable, in the long run, than a universe where everything remains perfectly uniform. But the complication, and this is where the discomfort begins, is that the universe's expansion is accelerating. About 1 billion years ago, perhaps more, the rate at which the universe is expanding began to increase. The driving force behind this acceleration is still not fully understood. Scientists call it dark energy, but that is a name for an ignorance, not an explanation. Whatever it is causing the vast distances between galaxies to increase faster and faster. This acceleration means that the energy radiated by stars is being carried away more quickly. It is being spread across a universe that is growing larger and larger. The photons released by stellar fusion are finding themselves in an increasingly vast cosmic void. This brings clarity to the original paradox. Stars are burning. They are releasing enormous amounts of energy. But that energy is not accumulating anywhere. It is not heating the universe in any global sense. The universe as a whole is getting colder because the expansion is winning against any concentration of energy. The universe expands, and as it does, the radiation from all the stars gets spread across more and more space, and the radiation from the background of the cosmos, the ancient light left over from when the universe was young and hot, gets redshifted to longer and longer wavelengths, which means lower and lower energies, which means lower and lower temperatures. The explanation appears complete. The stars burn, but their energy is carried away by an expanding universe. The universe cools because space itself is growing larger, and the same amount of energy spread across a larger volume means a lower temperature. The second law of thermodynamics is satisfied. Entropy increases. Heat flows from hot places to cold places. Order decays into disorder. But something does not settle. The resolution seems clean until one considers what happens at the very edge of perception. In the 1920s, an astronomer named Edwin Hubble made a discovery that changed how scientists understood the cosmos. He observed that distant galaxies were moving away from us, and moreover, the farther away a galaxy was, the faster it appeared to be receding. The universe was not static. It was expanding. This observation eventually led to the Big Bang theory, the idea that the universe had a beginning, that it emerged from an extraordinarily hot, extraordinarily dense state, and has been expanding and cooling ever since. But Hubble's observation contains something else, something that took decades to fully appreciate. If galaxies are moving away from each other, then in the past they must have been closer together. If one traces backward through time, following the expansion in reverse, one arrives at a moment when all of space was compressed into an infinitely small point. That moment was the Big Bang. At that instant, according to the calculations, the universe was infinitely hot and infinitely dense. There was no before. There was only this moment of infinite intensity, and then the expansion began. This creation scenario seemed to solve one problem while creating another. If the universe began in a state of infinite temperature and infinite density, then it began in a state of maximum entropy, infinite disorder, infinite disorganization. And yet, the universe we observe now, billions of years later, has structure. It has order. Stars exist. Galaxies exist. Life exists. How is this possible if the universe began in maximum entropy? The answer that emerged from cosmological research was surprising. The universe did not begin in maximum entropy. It began in minimum entropy. The initial conditions of the Big Bang were extraordinarily organized. The distribution of matter and energy was remarkably smooth. The temperature was uniform. In a universe with gravity, in our universe, has gravity, smoothness, and uniformity are actually states of very low entropy. Gravity causes matter to clump together. It causes dense regions to form. It causes structure to emerge. A universe that begins smooth and uniform will, over time, develop structure precisely because doing so increases entropy in a gravitational system. This inversion of intuition was articulated most clearly by Roger Penrose, a physicist who won the Nobel Prize for his work on black holes. Penrose asked a question that had haunted cosmology: why did the universe begin in such a low entropy state? Why was it so organized, so smooth, so orderly? The answer was not obvious. In principle, the Big Bang could have created a universe in any state. It could have created a universe that was already maximally disordered, with matter randomly distributed, no structure, no possibility for the emergence of complexity. But it did not. Something about the initial conditions of the universe imposed remarkable order. This is one of the deepest mysteries in physics, and it remains largely unsolved. What is clear is that the universe's subsequent evolution has been a matter of entropy increasing, of disorder growing, but in a way that looks like organization. Because gravity reverses the usual intuition about what high entropy states look like, the evolution of the universe has been a process of structure formation. The universe began smooth and ended up lumpy with stars and galaxies. And paradoxically, the lumpy universe has higher entropy than the smooth one would have had. But this still does not explain why the universe is getting colder, even as stars burn. The resolution of the paradox seems to be that the universe is expanding faster than stars can heat it. The expansion is winning. The cooling is inevitable. And yet, there is something incomplete about this picture. One can trace the energy. One can follow the radiation. One can confirm that the universe's temperature is indeed decreasing. The measurements are clear. Observations made by telescopes in the early 2000s showed that the average temperature of the universe has been dropping. Recent observations by the Euclid Space Telescope confirmed that star formation has already peaked. The rate at which new stars are being born has begun to decline. The universe is aging. It is cooling. The era of stars, in a sense, is beginning to end. But the real issue is not what was being explained through the conventional account of entropy and expansion. The real issue is a question that lurks beneath the surface, unasked. What does entropy actually mean when applied to the entire cosmos? In a laboratory, in a room, in any finite system, entropy is a useful measure. It tells how many microscopic arrangements are compatible with a macroscopic observation. It increases in isolated systems. It provides a direction for the arrow of time. But the universe is not a laboratory. The universe is not a finite system. The universe, as far as anyone knows, is all there is. There is no outside to it. There is no larger system containing it. When physicists apply the second law of thermodynamics to the universe as a whole, they are making an assumption. They are assuming that the universe can be treated as an isolated system, that it obeys the same rules as any closed thermodynamic system, that entropy in the universe always increases and approaches a maximum. But this assumption has never been rigorously proven. It has never been demonstrated from first principles that the second law of thermodynamics, derived from observations of small, local systems, applies to the universe in its totality. There is a conceptual gap, a leap. And on the other side of that leap is where things become less certain. Consider what entropy means in the context of the expanding universe. As space expands, the number of possible microscopic configurations available to the matter and radiation in the universe increases. This is simply because there is more space, more volume, more room for particles to be arranged in different ways. Entropy increases, but there is a complication. As space expands, the wavelengths of photons expand with it. Radiation gets redshifted, its energy decreases. The temperature of the background radiation falls, but the volume available increases. The product of these effects, lower energy density, in a larger volume, is what defines a cooling universe. This is where the picture becomes subtle. One can say the universe is cooling because expansion wins against stellar radiation. But one can also say the universe is cooling because the definition of temperature itself changes as space expands. Temperature in thermodynamics is ultimately a measure of the average kinetic energy of particles. But in an expanding universe, the energy of radiation decreases due to redshift. The meaning of temperature becomes ambiguous. What does it mean to talk about the universe's temperature when space itself is stretching? The answer that physicists have settled on is that the universe's temperature is defined by the temperature of the cosmic microwave background radiation, the ancient light left over from when the universe was young and hot, from a time only about 380,000 years after the Big Bang. When the universe was very young, this radiation was extraordinarily hot, with a temperature of thousands of Kelvin. As the universe expanded, this radiation got redshifted, and its temperature decreased. Today, about 13.8 billion years after the Big Bang, the temperature of the cosmic microwave background is about 2.7 Kelvin, just barely above absolute zero. This is considered the temperature of the universe. But here is where a subtle issue emerges. The temperature of the cosmic microwave background is not determined solely by the expansion of the universe. It is also affected by the energy input from stars. Every star that burns adds heat to the universe. Every star radiates energy that gets absorbed by dust, by gas, by space itself. One might expect that this energy input would slow the cooling process, would make the universe warm up slightly, would create a measurable counter effect to the expansion-driven cooling. Yet, measurements show no such effect. The universe continues to cool at the rate predicted by expansion alone. Stellar radiation has no measurable impact on the cosmic temperature. Why is this? The answer lies in the fact that stellar radiation is not distributed uniformly. Most of the energy from stars gets absorbed by dust and gas in galaxies. It heats those regions locally. But on the largest scales, on the scales of billions of light years, the universe remains remarkably smooth and uniform. The stellar radiation, massive as it is in absolute terms, is utterly negligible on cosmic scales. A single star, the Sun, radiates 386 billion megawatts. All the stars in a galaxy, maybe 100 billion stars on average, radiate something like 10 billion megawatts. All the galaxies in the observable universe, numbering perhaps 200 billion, would radiate an almost incomprehensible amount of power. And yet, spread across the vast distances between galaxies, this energy is diluted to insignificance. The universe's temperature is determined not by the stars, but by the background radiation of space itself, radiation that is constantly being redshifted to lower and lower energies as the universe expands. This realization introduces a new layer of discomfort. The stars are not irrelevant to the universe's future, but they are irrelevant to its temperature. They burn. They create light and heat and complexity. They seed planets and enable the emergence of life. But they do not change the temperature of the universe. They do not alter the cosmos's fundamental trajectory toward cold and dark and empty. They are, in a sense, local phenomena, intense and bright and organized, but ultimately minor notes in the overall cooling of space. Their energy, tremendous though it is, disperses into a universe so large that it leaves barely a trace. In the early 20th century, before expansion was understood, before the Big Bang was proposed, before the cosmic microwave background was discovered, physicists who thought about heat death imagined a scenario where the universe gradually cooled as all the energy from stars and other sources got radiated into space and the cosmos approached equilibrium. The vision was of a slowly darkening cosmos, with stars winking out one by one, with the universe settling into quietness and cold. This picture is correct in its essential outline, but it misses something important. The universe is not cooling gradually. It is cooling exponentially, driven by the expansion of space itself. Stars and all the complexity they enable are happening against a background of accelerating cooling. The more the universe expands, the faster it cools. The more time passes, the fewer stars there are left to burn. The future is not just cold, it is increasingly cold, increasingly dark, increasingly empty. What emerges is a cosmos in which the thermodynamic arrow of time is not just pointing toward disorder, it is pointing toward erasure. Every process that generates heat, every reaction that creates order, every star that burns, is happening within a universe that is inexorably expanding, cooling, and moving toward a state of perfect thermal uniformity from which nothing can recover. The stars do not fight this process, they accelerate it. They concentrate energy, burn it, and radiate the aftermath back into space. They are not exceptions to the second law of thermodynamics. They are the mechanism through which the second law is enforced. At this point, the explanation would normally resolve, a narrative arc would close. The paradox would be answered. The universe gets colder, even as stars burn, because expansion carries away the energy faster than stars can produce it, and stellar radiation is negligible compared to the vastness of space. The mechanism would be clear. Understanding would be complete, but understanding has not arrived. Something has shifted instead. The question that began as "why is the universe getting colder?" has transformed into a deeper one. What does it mean for a universe to have a temperature at all? Temperature is a concept born from human experience. It describes the sensation of hot and cold, the measure of molecular motion, the degree of kinetic energy in a substance. In a room, temperature is well defined. In a star, temperature is clear, but in the universe as a whole, the concept becomes slippery. The cosmic microwave background has a temperature of 2.7 Kelvin. This number is measured, confirmed, real, and yet it is not the temperature of everything. Pockets of the universe are far hotter. The cores of stars reach millions of Kelvin. The accretion disks around black holes reach billions of Kelvin. Near the Big Bang itself, the universe was infinitely hot. So when someone says the universe is cooling, what precisely is being measured? The universe is not a uniform object with a single temperature. It is a collection of regions with vastly different temperatures. What changes is the average, the background, the overall envelope within which all local events occur. This background is set by the cosmic microwave background radiation, the ancient light that has been traveling through space since the universe was only 380,000 years old. For billions of years, this radiation has been the thermometer of the cosmos. As the universe expands, this radiation gets redshifted, its temperature drops, and the universe cools. But there is a subtlety here that has never been fully resolved. The cosmic microwave background does not cool because the universe is losing energy. Energy is conserved. The cosmic microwave background cools because the same energy is being spread across an increasingly large volume. The photons are not disappearing. They are being stretched. Their wavelengths are increasing. Their energies, by the relation E equals hf, are decreasing proportionally. But here's what remains unresolved. This stretching of photons is not a physical process in the conventional sense. It is not friction. It is not radiation into a surrounding medium. It is a consequence of the geometry of spacetime itself. Space is expanding. The metric of spacetime, the mathematical description of how distances are measured, is changing. Photons are not being stretched by forces acting upon them. The definition of a meter, the meaning of a wavelength, is changing as space itself expands. The temperature of the universe is decreasing not because energy is dissipating into some environment beyond the universe. There is no such environment. Temperature is decreasing because the very concept of distance, and therefore wavelength, and therefore energy per photon, is being redefined by the expansion of spacetime itself. This introduces a profound asymmetry in how entropy should be understood in the cosmos. In conventional thermodynamics, entropy increases because energy disperses, because systems move toward equilibrium, because disorder is more probable than order. But in an expanding universe, entropy increases not only through these familiar mechanisms, but through something else entirely, through the stretching of space itself. The universe's evolution toward heat death is not just a matter of thermodynamic dissipation, it is also a matter of geometric transformation. Space is reshaping itself in a way that guarantees entropy will increase, that energy will be diluted, that heat will be spread ever thinner across ever larger volumes. What then of the stars? Their burning adds local heat, local order, local complexity. But it does nothing to stop the geometric transformation of space. A star burning in an expanding universe is like a candle burning in a room that is itself expanding, becoming larger, colder, emptier. The candle does not warm the room. The flame does not reverse the expansion. The candle simply exists, burning for a time, and then goes out, and the room continues to expand, and continues to cool. There is a final layer to this understanding that has not yet been articulated clearly. The reason the universe began in a state of low entropy, the reason it started smooth and organized, remains one of physics' deepest mysteries. Various proposals have been made. Some scientists suggest that the Big Bang's special initial conditions were a cosmic accident, an unlikely event that simply happened to occur. Others propose that the universe's beginning is connected to quantum mechanics, that the wave function of the universe somehow determines the initial state. Still others, like Roger Penrose, have suggested that the universe might be part of a larger infinite structure where universes are continually being created from the remnants of previous ones, each inheriting the low entropy conditions from the black hole singularities of its predecessor. None of these proposals is conclusive. None has been proven. The mystery of why entropy was low in the past, why the universe began organized instead of already at maximum disorder remains open, and it will likely remain open. The universe does not leave records of its own creation. The cosmic microwave background, the oldest light we can observe, comes from a time only 380,000 years after the Big Bang, long after the universe's initial conditions were set. The universe's beginning is, in a real sense, inaccessible to observation. What remains is a universe moving toward heat death, driven by expansion and entropy increase, with stars burning bright against the encroaching cold, and with no clear explanation for why the initial conditions made such burning possible in the first place. The universe will continue to cool. The era of stars will end. The galaxies will grow dim. Black holes will eventually evaporate through Hawking radiation, their mass converted to photons that escape into an increasingly vast and cold cosmos. The final state will be one of maximum entropy, a diffuse gas of elementary particles and radiation at nearly absolute zero, spread across an infinite volume, with no structure, no heat flow, no possibility for change. This state is not a prediction. It is a conclusion derived from the second law of thermodynamics and the geometry of an expanding universe. It does not require proof. It is almost inevitable, but the limit that defines this future, the inexorable progression toward cold and darkness, no longer means what it seemed to mean at the beginning. It is not simply a consequence of thermodynamic dissipation, of energy spreading out and becoming unavailable. It is a consequence of space itself transforming, of geometry redefining what energy and temperature mean, of the universe evolving not toward equilibrium in any conventional sense, but toward a state of maximum entropy in a space-time that is continuously reshaping itself. The stars burn. They will burn for billions of years more, creating light and heat and the conditions for life. But they do not warm the universe. They cannot. The universe is not warming or cooling in response to their burning. The universe is cooling because space expands. And space expands not because of anything the stars do, but because of something inherent in the structure of space-time itself, something written into the geometry at the moment of creation, something that continues to unfold regardless of what happens within it. The limit remains. But it no longer means what it seemed to mean. It does not close.